This podcast talks about the different types of acids and bases and how we label them, and the three common definitions that we are going to use. So the three types of acids and bases are Arrhenius, Bronsted-Lowry, and Lewis. So Arrhenius acids and bases are historically the first ones that were defined, and chemists who studied, very early chemists who studied their behavior, defined acids and bases by their behavior in water, and said that an acid had to lose a proton or supply a proton in water, and that an Arrhenius base would lose a hydroxide in water. And these are the acids and bases that we have actually been looking at so far. We say, oh, it has a proton, it's an acid. It has a hydroxide, it's a base. And then we use these concentrations to calculate the pH. So what we've been looking at so far are Arrhenius acids and Arrhenius bases. And this definition works really, really well for lots and lots of acids and bases. However, there was a problem with this definition, not really with acids, but some bases, for example, ammonia, which is a really common base, and sodium carbonate, Na2CO3, look at these formulas for bases. We know that they are basic. However, they don't have a hydroxide. In their formula. So these did not fit the definition of acids and bases, and they needed to broaden the definition a little bit. So then that led to the next definition, which we call the Bronsted-Lowry definition of acids and bases. And it says that acids are proton donors and bases are proton acceptors. So bases don't have to have a hydroxide. However, they do have to be able to accept a proton. And this really is our most common definition when we talk about reactions of acids and bases, and being able to follow the proton around and see where it goes. So if you have an acid plus water, then the acid is going to give up its proton to water and make the anion and H3O+. So in this case, we have an acid, and because water accepts a proton, water acts as a base. If we have a strong base, or a base that we add to water, the base accepts a proton and becomes BH+, the water gives a proton and becomes hydroxide. So with a base, water acts as an acid. So in this definition, it's not really defined by the formula, what the formula looks like. Acids and bases are defined by what they do with protons. So water is really special. Water is what we call amphoteric, which means it can act as an acid or a base, and it does so very commonly depending on what it's with. There are other compounds and other substances that are also amphoteric, but water is definitely the most famous and the most common amphoteric substance. So look at these acids or bases, figure out, use our old method. Look, if they have a proton, they're going to be an acid. Ammonia, NH3, is going to be a base. And you're given a hint here. This stuff here is this is sodium hypochlorite, which is bleach, which is a base. And use what you know to figure out what it's going to do with water. So the acids, like HI, are going to lose a proton, and then water is going to act as a base. The bases, like ammonia, are going to accept a proton, and the water is going to act as an acid. So again, we see that water can flip-flop, can do either depending on what it's with. Sodium hypochlorite does a little bit of a weird thing. It is a base, so it picks up a proton from water. And notice that so these Bronsted-Lowry bases don't have hydroxide in their formula, but when we put them into water, because water gives up a proton, acts as an acid, then they create hydroxide in solution. So this is why they raise the pH, even though they don't have a hydroxide in their formula. The last definition of acids and bases is the Lewis acids and base. And in this case, there were some acids that didn't fit the proton definition, and that's how this definition came to be. So instead of defining an acid base by protons, a base is a lone pair donor, and an acid is a lone pair acceptor. So an acid does not have to have a proton, but it has to be able to accept a lone pair. When you have a Lewis acid-base reaction, it's going to make something that we call an adduct, A-D-D-U-C-T. So we are going to look at a reaction, and what you have to be able to do is label it according to what is the Lewis acid and what is the Lewis base. So we'll look at the first one. Type it right there. Good enough. We'll look at the first one, and BF3, which does not have a lone pair on the boron, remember, does a reaction with ammonia, and it makes this big compound. Here's the new bond that got formed. We call this a coordinate covalent bond, and the electrons from this new bond came from the nitrogen in ammonia. And so because nitrogen donated the electron pair, it is the Lewis base. It's the electron pair donor. And BF3 is the electron pair acceptor, so it is the Lewis acid because it made a new bond, but it did not donate any electrons. The next reaction is sulfur dioxide, which is SO2, and it reacts with water, H2O, and it makes this complex here. Again, this new bond formed is the coordinate covalent bond. And if you count up all the electrons and account for them, you'll realize that the electrons in the new bond came from the oxygen. So oxygen is the lone pair donor, so it's the Lewis base. And sulfur, SO2, is the lone pair acceptor. Even though it does have a lone pair, the new bond didn't come from this lone pair, it came from the oxygen in water. So sulfur is the Lewis acid. So you have to sort of follow the electrons around and figure out what did the donating, that's the Lewis base, what did the accepting, that's the Lewis acid, and be able to label. You don't have to be able to predict what the product is going to be, but you have to be able to look at the reaction, the whole reaction, and label the Lewis acid and the Lewis base.